why can nothing travel faster than light? This question sounds simple, but it leads to one of the deepest ideas in modern physics. In everyday life, we can keep pushing an object to make it move faster. A car can go faster. A rocket can go faster. A particle accelerator can push particles to incredible speeds. But according to special relativity, there is a final speed limit. That limit is the speed of light in vacuum. In this video, we will explain why objects with mass can get closer and closer to light speed, but can never reach or exceed it. Here is what this video will explain. First, we will look at the speed of light in vacuum. Then, we will see Einstein's key insight: the speed of light is the same for all observers. Next, we will explore what happens as speed increases. We will also see why more and more energy is needed to go faster. Then, we will explain why objects with mass cannot reach light speed. Finally, we will see where this speed limit matters in real physics and technology. The main idea is simple: light speed is nature's ultimate speed limit. The speed of light in vacuum is usually represented by the symbol c. Its value is about 300 million meters per second. More precisely, it is 299,792,458 meters per second. This is not just the speed of visible light. It is also the speed of all electromagnetic waves in vacuum, including radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. In special relativity, c is not just a large number. It is built into the structure of space and time. Einstein's key insight was that the laws of physics are the same for all observers moving at constant velocity. This means that no observer in uniform motion has a special claim to being absolutely at rest. Einstein also showed that the speed of light in vacuum is the same for all such observers. This is very different from ordinary motion. If you throw a ball forward from a moving train, a person on the platform measures a different speed from a person on the train. But light does not behave like that. Every observer measures the same speed of light. Because light speed stays fixed, measurements of time, length, and energy must adjust. At low speeds, motion behaves almost exactly as Newton's physics predicts. If we apply a force, the object speeds up in a familiar way. But as the object moves faster and faster, especially close to the speed of light, relativistic effects become important. Time dilation becomes stronger. Length contraction becomes stronger. The relationship between energy and speed also changes dramatically. Adding energy no longer produces the same increase in speed as before. The object can still gain energy, but its speed approaches light speed more and more slowly. Near light speed, more energy gives less and less extra speed. To make an object with mass move faster, we must add energy. At ordinary speeds, this seems straightforward. More energy means more speed. But near the speed of light, the energy required rises extremely sharply. The closer an object gets to light speed, the more difficult it becomes to increase its speed further. To reach the speed of light exactly, an object with mass would need infinite energy. And infinite energy is not physically available. That is why massive objects can approach light speed, but cannot reach it. An object with mass has inertia. Inertia means it resists changes in motion. As the object moves faster, special relativity tells us that its total energy increases. At speeds close to light speed, the energy becomes enormous. If we try to push the object all the way to light speed, the required energy grows without limit. This is why a spaceship, a planet, a person, or any object with rest mass cannot travel at the speed of light. It can get very close, in principle. But it cannot reach c. Massive objects are always limited to speeds below light speed. So what can travel at the speed of light? Light itself travels at c in vacuum. The particles of light are called photons. Photons have no rest mass, so they do not need to be accelerated from rest to light speed. They always travel at the speed of light in vacuum. Electromagnetic waves also travel at c in vacuum. This includes radio waves, microwaves, visible light, X-rays, and gamma rays. Massless particles, if they exist or are observed, must travel at light speed. Objects with mass move below c. Massless radiation travels at c. A common science fiction idea is faster-than-light travel. It is easy to imagine a spaceship simply becoming faster and faster until it crosses the speed of light. But in special relativity, this cannot happen for any object with mass. The problem is not only engineering. It is not just that our rockets are not powerful enough. The deeper issue is that the structure of spacetime prevents massive objects from reaching or exceeding light speed. To reach c would require infinite energy. To go beyond c would violate the way cause and effect work in relativity. Faster-than-light travel is not allowed for objects with mass in our current understanding of physics. The speed of light matters in many areas of real science and technology. In GPS systems, relativity must be included so satellites can give accurate positions on Earth. In particle accelerators, particles are pushed to speeds extremely close to light speed, but never beyond it. In astronomy, light from distant stars and galaxies takes years, millions of years, or even billions of years to reach us. So when we look far into space, we are also looking back in time. Modern communication also depends on signals that travel at, or close to, the speed of light. The speed of light shapes how we measure distance, time, energy, and information. Let us now gather the key idea. The speed of light in vacuum is not just a very fast speed. It is a fundamental limit built into the structure of spacetime. Objects with mass can move faster and faster as energy is added. But as they approach light speed, the energy required grows without limit. That is why massive objects can never reach or exceed the speed of light. Light and other massless radiation travel at this speed in vacuum. The key takeaway is simple: light speed is nature's ultimate speed limit. Thank you for learning with Prep for Uni Online. If you want to understand special relativity more deeply, continue with our lessons on time dilation, length contraction, E equals mc squared, spacetime, and modern physics. Prep for Uni Online provides free university preparation resources for students exploring science, technology, engineering, mathematics, humanities, business, health, and the arts. Our goal is to help students build strong foundations before university study. Visit Prep for Uni Online and continue your learning journey.